All right, so we've looked at the definition of the derivative or the first principles idea. Let's look at how we could use this then to differentiate a function, okay? We want to find the rate of change of this parabola at x equals 4. All right, if I did a quick sketch of this.
Oh, is this day 4?
Yeah, we kind of finished day 3, you got into day 4 here. Okay? We want to find the rate of change at x equals 4. Now this has a y-intercept at -5.
Did you know if you draw the line and hold your pen down, it's going to make it like...
This is a different program.
Oh.
I'm using...
Sorry.
That's okay. Thanks, though. So we've got this point here. Our zeros are going to be... something like -3 plus or minus 9 plus 20, so square root of 29 over 2. So that's like 5.3 or something. So that's going to be about at 1 point something. So here's a 0. And
Here, are you sure? Did you just find a 0?
yeah.
What was that?
I'm trying to find, that's the quadratic formula. Okay.
It's negative b plus or minus b.
All right, so we've got a positive 1 point something and a negative like 4 point something. Okay, so it's going to be here. We don't have to have the exact. Okay, I'm just sketching this here to get kind of an idea of what it should be like. All right, so if I see my parabola and it looks like this, okay, what do I know about the slope at x equals 4?
At x equals 4?
Yeah, it's going to be somewhere over here.
Well, the slope's positive, yeah.
Yeah, the slope of the tangent line, here's our tangent line. That's the slope I'm looking for, okay? Our slope for this line is going to equal the derivative evaluated at 4, okay?
So we have to input 4 into the derivative formula?
Yeah, we want to find the derivative first, and then we're going to input 4 into that formula, okay?
Yay.
Now, so let's see, that'd be, by the way, that's the point 4, and then let's see, 16 plus 12 is 28 minus, that's 23, okay? So, none of this yet is the derivative. So let's actually look at what we need to find the derivative here. First of all, notice our function uses f of x plus delta x, okay? I would recommend specifically at this point, or especially at this point, when you're first learning to use this, write down your f of x plus delta x separately and simplify it first before you start plugging it into your formula. Okay? So, I'm going to put in an x plus delta x right here, so that's squared, plus 3 times x plus delta x minus 5. Notice, I'm not just putting an x plus delta x in a formula, I'm actually evaluating the function at x plus delta x. Okay? So if I simplify this, I've got to FOIL x squared plus 2x delta x plus delta x squared plus 3x plus 3 delta x minus 5. Okay? Now, there aren't any like terms here that I can combine, so that's simplified. So now we're ready to plug that into our definition of the derivative. Okay? So, we have here the limit as delta x approaches 0 of the f of x plus delta x that we just found. So x squared plus 2x delta x plus delta x squared plus 3x plus 3 delta x minus 5. Okay? So that's just this part right here. So now I need to subtract the original function. So minus x squared plus 3x minus 5. Okay? And this whole thing here is over delta x. Okay? Now, here's the problem, okay? Let's simplify this a little bit first of all. I have an x squared minus an x squared, right? So that's gone. Let's cancel that out here. So minus the x squared cancels out the x squared.
3x and, yeah, 3x's.
Good, 3x minus, because we're distributing the negative, minus 3x.
And the -5 and the -5.
Good, the -5, and we distribute that, so it's a plus 5, so that cancels out to 0. Okay? And notice what we end up with left. We have the limit as delta x approaches 0 of 2x delta x plus delta x squared plus 3 delta x all over delta x. Now, what do I get if I evaluate for delta x equals 0?
You can pull the delta x out.
Undefined.
Why is it undefined, Ben?
Because it's 0 over 0.
Yeah, it's 0 over 0, okay? This is what's known as the indeterminate form.
Because it's
Indeterminate form. 0 over 0. So how do we handle an indeterminate form? And here's the thing. Every one of these is going to turn out to be an indeterminate form. Okay? So we have to know how to handle these. The way you can handle these, sometimes you get them when you have radicals. So one thing you would do is rationalize your denominator, and that'll help. Okay? But in this case, though, what do you notice about our numerator?
Pull out the old delta x.
Yes, good. The numerator has a common factor of delta x. So we have 2x plus, now it's just delta x to the first, plus 3. And this whole thing is over delta x. So we find here actually that thankfully delta x doesn't provide us with an asymptote. Delta x provides us with a whole, because this will cancel out. So the nice thing is you still can take the limit, because as you cancel out the whole, you can find where this function is approaching. Okay? So now I can take the limit as delta x approaches 0 of 2x plus delta x plus 3, and this is a function that I can simply evaluate. Okay? Because now when I plug in 0, I get 2x plus 3. So that is f prime of x. Okay? Now guys, the nice thing about this is they all work pretty much the same. Okay? After you do the f of x plus delta x minus f of x, all of the terms that you have left over should have that delta x so that you can cancel it out. Okay? You can pull it out and cancel it out. Alright? Now, there are other functions, more complicated functions, where it's a little bit more challenging to do that. Okay? For our purposes, we only need to be able to really handle polynomial functions this way. Okay? Now, at this point, we can actually find what we were looking to find. What is the rate of change of our function when x equals 4? What'd you say?
Oh, yeah, it's 11. I can't.
Okay, how are you getting this?
21 for x.
Yeah. Now we just have to do f prime of 4. So 2 times 4 plus 3 is 11. Okay? So that's the rate of change at that specific point. Okay? Now, there's a couple of reasons why we might want to do this. For one, if we were talking about some sort of motion, or if we were talking about, a real life kind of scenario, we could relate it to the situation pretty easily here. Okay? Another case, though, is finding a normal line or finding the equation of the tangent line. Okay, there are a couple applications. We're going to look at these here in the near future. All right, but at this point, since I know the slope of the tangent line and I know the point of tangency, I could find the equation of that tangent line, right? I could use point slope form now and find the equation of that tangent line. You all with me? That make sense? Okay. Also, there's something called the normal line. The normal line is a line that's perpendicular to a curved surface. Okay, this is used a lot when they're designing lenses or curved mirrors, satellite dishes, all of those types of things. We want a normal line to figure out what the angle of incidence is, so we can figure out what the angle of reflection will be. Okay. So the normal is perpendicular. So now if I wanted to find the normal line at the point 423, I would just find the slope that's perpendicular to this one, which would be what?
Negative 1.5.
Negative 1 over 11.
Wait, how did you find 23?
What's the slope?
2.
No, what's the slope at 4?
Oh, true.
It's 11, right?
It's true.
So the normal line at the point 423 would have a slope of negative 111.
Wait, I'm confused. How did you get 23?
I just plugged it into my equation. 4 squared plus 3 times 4 minus 5.
Oh,
That's just a point on the graph.
okay.
Okay, so that's the point. At this point, I know the rate of change is 11. Okay. All right, let's try here. Okay, x cubed. X cubed. So first things first, I'm going to put in x plus delta x. So now I have x plus delta x cubed. And since you guys all know how to do the binomial expansion, this is a piece of cake, right?
Yeah.
Of course. So you have 1, 3, 3, 1 as your coefficients. And then you have x, not delta, x cubed, x squared, x, and no x's, delta x cubed, delta x squared, delta x, and no delta x's. Okay, so there's our f of x plus delta x. So now we're plugging this into our definition of a derivative. Okay, so here's f of x plus delta x. Okay, minus the original function, which is just x cubed, all over delta x. Okay, so what happens here?
You can cancel out the x cubes.
Yeah, cancel out the x cubes because you subtract. Okay. All right, and that's all over delta x. So now what? Take out the delta x and cancel it out, okay? So let's do that here. We got a delta x here. We've got delta x squared, so now that's going to be delta x to the first. Here's a delta x cubed, so now that's going to be delta x squared, and all those will cancel with that. So we're taking the limit of 3x squared plus 3x delta x plus delta x squared. And now we can evaluate. So what does our derivative equal?
3x squared.
Yeah. 3x squared. Okay. So what's our rate of change at x equals 4?
48.
48, yeah. F prime of 4 is going to be 3 times 4 squared, so that's 48. Okay?
Wanna hang on